Hello there, and welcome to a quiet journey through deep time. Tonight we're going to explore something remarkable and distant, something that happened long before humans walked the earth, before cities, before forests as we know them, even before the familiar shapes of our continents. We're going to visit a world that existed between 299 and 180 million years ago, a world where all the land on Earth was joined together in one enormous mass. Scientists call this ancient supercontinent Pangea. The name comes from ancient Greek words meaning all Earth. Can you imagine what our planet looked like then? Picture all the continents you know today pushed together like pieces of a giant puzzle. North America pressed against Europe, South America tucked beside Africa, Australia and Antarctica joined as one, all of it forming a single massive landmass surrounded by one great ocean. This wasn't just a different arrangement of familiar places, this was an entirely different world. The air was different. The climate was different. Even the length of a day was different. Time itself moved to a different rhythm in the age of Pangea. Scientists believe Pangea existed for about 120 million years. That's a span of time so vast it challenges our imagination. To put this in perspective, humans have only existed for about 300,000 years. All of recorded human history spans roughly 5,000 years. Pangea lasted thousands of times longer than our entire species has existed. How do we know about this ancient world? The story begins with a German scientist named Alfred Wegener. In the early 1900s, Wegener noticed something curious about maps of the world. The coastlines of distant continents seemed to fit together. The eastern edge of South America appeared to match the western edge of Africa. The bulge of Brazil looked like it could nestle perfectly into the curve of West Africa. Wegener wasn't the first person to notice this, but he was the first to seriously investigate what it might mean. He began collecting evidence from rocks, fossils, and ancient climate patterns. Slowly, carefully, he built a case for something that seemed impossible at the time. He proposed that the continents had once been joined together and had somehow drifted apart. Most scientists of his era dismissed Wegener's ideas. They couldn't understand how massive continents could move across the Earth's surface. The notion seemed too fantastic to believe, but Wegener persisted, gathering more evidence, refining his theories. He spent his life trying to convince the scientific world that the Earth's surface was not fixed and permanent. It would take decades after Wegener's death for scientists to understand how he was right. The discovery of plate tectonics in the 1960s finally explained how continents could move. The Earth's outer shell, it turned out, consists of moving plates of rock. These plates drift slowly across the planet's surface, carrying the continents with them like passengers on enormous rafts. This movement happens incredibly slowly. Continental drift occurs at roughly the same rate that your fingernails grow. In a human lifetime, continents might move a distance of about 1.8 meters. Over millions of years, however, this slow motion can transport land masses across entire oceans. The story of Pangea is really the story of these moving plates coming together. For hundreds of millions of years before Pangea formed, smaller continents and land masses had been wandering around the globe. Gradually, over vast periods of time, they began to collide and stick together. Scientists think the assembly of Pangea happened in stages. First, two large land masses called Gondwana and Euramerica came together. Then a third piece called Siberia joined them. Finally, smaller fragments and island chains were added to complete the supercontinent. The entire process possibly took 100 million years. Think about that timeline for a moment. The formation of Pangea took longer than the entire age of dinosaurs. It took longer than the time between the first appearance of complex life and today. Mountains rose and eroded away. Oceans opened and closed. Countless generations of creatures lived and died while this slow motion collision continued. When Pangea was fully assembled, it stretched from pole to pole. No other landmass in Earth's history has been quite so large or so dominant. The supercontinent covered about one-third of the planet's surface. The rest of the Earth was ocean, one vast world-spanning sea that scientists call Panthalassa. This arrangement created conditions unlike anything we see today. Weather patterns were different. Ocean currents followed different paths. The very rhythm of seasons changed across much of the supercontinent. Life on Pangea faced challenges and opportunities that no longer exist in our modern world. The creatures that lived during Pangean times would seem alien to us today. Some were the ancestors of animals we know now. Others belonged to evolutionary experiments that ended without descendants. They lived under different skies, breathed different air, and experienced seasons and weather patterns that have no modern equivalent. Yet in many ways, Pangea was still recognizably our Earth. The same physical laws governed its climate and geology. The same processes of erosion, volcanic activity, and mountain building shaped its landscapes. Water still flowed downhill. The sun still provided energy for life. The moon still pulled the tides. As we begin our journey through Pangean time, it helps to remember that this ancient world was both strange and familiar. Strange because its geography, climate, and life forms were so different from today. Familiar because it was built from the same raw materials and governed by the same natural forces that shape our modern planet. Tonight, we're going to explore this lost world together. We'll walk across its vast interior deserts and sail its ancient seas. We'll climb its towering mountains and witness its extraordinary weather patterns. We'll meet the creatures that called it home and understand how they adapted to its unique conditions. Most importantly, we'll discover how Pangea's story connects to our own. The rocks beneath our feet, the mountains on our horizons, even the Atlantic Ocean that separates Europe from America, all carry traces of the Pangean world. Understanding this ancient supercontinent helps us understand our own planet and our place in the long story of Earth's history. So settle in comfortably and let your imagination drift back through the centuries and millennia. Let it carry you across 200 million years to a time when the world looked nothing like it does today. Let it take you to the age of Pangea, when all land was one and our Earth told a very different story. The journey we're about to take spans more time than the human mind can easily grasp, but that's part of its wonder. In exploring Pangea, we're not just learning about ancient geography, we're touching something profound about the nature of time itself and our planet's capacity for change. As we continue our journey, we'll discover how this great supercontinent came to be assembled from the scattered pieces of an even more ancient world. Pangean assembly wasn't a sudden collision, but rather a slow choreography of continents, a patient gathering that unfolded over time, spans that dwarf human comprehension. Long before Pangea existed, The Earth's land was divided into several large pieces. Scientists call these ancient landmasses by names that might sound unfamiliar. Gondwana, Euramerica, and Siberia were the main players in this slow motion drama. Each carried within it the seeds of continents we recognize today. Gondwana was perhaps the most impressive of these early supercontinents. It included what would eventually become South America, Africa, Antarctica, Australia, and India. Picture these familiar places joined together in one enormous landmass. Gondwana stretched across the southern hemisphere like a giant puzzle piece, slowly drifting northward through ancient seas. Meanwhile, in the northern parts of our planet, another large landmass called Euramerica was taking shape. This continent combined much of what we now know as North America and Europe. The mountains of Scotland were pressed against the highlands of Greenland. The coal forests of Pennsylvania grew alongside the river valleys of Wales. Far to the east, the continent of Siberia wandered almost alone across vast oceanic spaces. This landmass carried within it the heart of what would become Northern Asia. It drifted like an enormous island, gradually making its way toward its future continental neighbors. The story of how these three great landmasses came together spans roughly 100 million years. It began during a time period scientists call the Carboniferous, around 350 million years ago. The name comes from the carbon-rich coal deposits that formed during this era from vast swampy forests. During the Carboniferous period, the Earth was quite different from today. The climate was generally warm and humid in many places. Enormous fern forests covered much of the low-lying land. These weren't the small ferns we see today, but tree-sized giants that created dense, steamy jungles. When these forests died and were buried, they eventually became the coal deposits we find today. It was against this backdrop of ancient forests and warm seas that the Great Continental Assembly began. Gondwana and Euramerica started moving toward each other first. The collision happened gradually, possibly over 50 million years. Mountain ranges rose where the two land masses pressed against each other. Vast areas of seafloor were squeezed upward to become dry land. Think about the forces involved in such a collision. These weren't small islands bumping together. These were continent-sized pieces of the Earth's crust, each one thousands of miles across. When they met, the impact created mountain ranges that possibly reached heights comparable to today's Himalayas. The evidence of these ancient collisions still exists today. The Appalachian Mountains of North America tell part of this story. So do the Caledonian Mountains of Scotland and Norway. These ranges were born from the slow but irresistible meeting of ancient continents. Over millions of years, rock layers were folded, lifted, and transformed by the incredible pressures of continental collision. Scientists believe the joining of Gondwana and Euramerica created what they called the Central Pangean Mountains. This was likely one of the most impressive mountain ranges in Earth's history. It stretched for thousands of miles across the newly assembled supercontinent. The range probably influenced weather patterns across much of the planet. As Gondwana and Euramerica were completing their slow merger, Siberia began its own journey toward the growing supercontinent. This collision came later, during the Permian period, around 280 million years ago. When Siberia finally joined the growing landmass, it completed the assembly of Pangea. The collision that added Siberia to the supercontinent created another impressive mountain range. Scientists call this the Ural Mountains, and remnants of this ancient range still exist in modern Russia. These mountains marked the boundary between what had been Europe and Asia, though those geographical distinctions didn't exist yet. Each of these continental collisions involved not just the creation of mountains, but the elimination of entire ocean basins. Ancient seas that had existed for millions of years were slowly squeezed shut. Their sediments were compressed and uplifted to become new mountain ranges. Marine creatures that had lived in these vanishing oceans left their fossils in what became high mountain peaks. The process wasn't always smooth or predictable. Sometimes continents approached each other and then pulled apart again before finally joining. Island chains and smaller land masses were swept up in these collisions, adding their own geological signatures to the growing supercontinent. Volcanic activity accompanied many of these tectonic events, adding layers of lava and ash to the geological record. What's remarkable about this assembly process is that it happened so slowly that no single generation of creatures would have noticed it. A carboniferous fern growing in the forests of Euramerica would have lived its entire life without detecting any movement toward Gondwana. The mountains rose at rates measured in millimeters per year. Seas closed at speeds invisible to any living observer. Yet, over the vast spans of geological time, these tiny movements accumulated into transformations that reshaped the entire planet. Ocean currents changed their patterns as seaways opened and closed. Climate zones shifted as land masses moved to different latitudes. The very distribution of life on Earth was altered by this slow continental dance. Scientists study this ancient assembly process through several types of evidence. Rock formations that match across oceans provide clues about which pieces were once joined together. Fossil distributions tell similar stories. Ancient creatures found in rocks on different continents suggest those lands were once connected. Magnetic signatures locked into rocks during their formation help scientists track how continents moved and rotated over time. The Central Pangean Mountains created by this assembly may have been among the tallest peaks our planet has ever seen. Some scientists think parts of this range might have reached elevations of 6 kilometers or more. These mountains would have cast rain shadows across vast areas of the supercontinent, creating deserts in their lee while trapping moisture on their windward sides. The formation of such massive mountain ranges also affected the chemistry of the Earth's oceans and atmosphere. The weathering of these new mountains consumed carbon dioxide from the atmosphere, possibly contributing to climate cooling during certain periods. The erosion products from these peaks were carried by rivers to distant seas, affecting marine ecosystems across the globe. As the assembly of Pangea neared completion, the Earth began to look more and more like the single continent world that would dominate our planet for the next 100 million years. The Great Gathering was almost finished. 3 ancient continents had become one enormous landmass that stretched from pole to pole. This wasn't just a change in geography, it was a fundamental restructuring of how our planet worked. Ocean circulation patterns were simplified. Climate became more extreme in many areas. Life on land faced new challenges and opportunities as migration routes opened across vast distances, while others were blocked by new barriers. The completion of Pangea's assembly marked the end of one chapter in Earth's history and the beginning of another. For the first time since the early days of continental formation, most of our planet's land was united in a single massive supercontinent. This would create conditions unlike anything that had existed before or that has existed since. Moving forward in time, we'll explore what this completed supercontinent actually looked like and how its distinctive shape influenced everything from ocean currents to weather patterns across the ancient Earth. Pangea had a distinctive shape that scientists often describe as resembling the letter C. This wasn't a neat, compact circle of land, but rather a sprawling, curved continent that stretched from the North Pole all the way to the South Pole. The supercontinent was widest near the equator and narrower toward both poles. The eastern side of Pangea curved inward, creating a huge bay or gulf that penetrated deep into the supercontinent. Scientists call this ancient sea the Tethys Ocean. Picture a bite taken out of an apple, and you'll have some sense of how the Tethys Sea curved into Pangea's eastern shore. This wasn't just a small inlet, but a major oceanic feature that influenced climate and life across much of the supercontinent. Building on this understanding of how Pangea assembled itself, we can now picture what this completed supercontinent actually looked like. Imagine looking down at Earth from space 250 million years ago. You would see something remarkable and strange, one enormous landmass surrounded by a vast, unbroken ocean. The western shore of Pangea faced the vast world ocean that scientists call Panthalassa. This name comes from ancient Greek words, meaning all ocean. Panthalassa covered roughly two-thirds of the Earth's surface. To put this in perspective, our modern Pacific Ocean is large, but Panthalassa was much larger. It stretched almost completely around the globe. If we could take a journey across Pangea from west to east, we would cover distances that seem almost impossible to imagine. The supercontinent measured roughly 10,000 miles from its western shore to its eastern shore. That's about 4 times the width of the United States. A journey from the northern tip of Pangea to its southern tip would cover even more ground, possibly 12,000 miles or more. To help visualize Pangea's size, consider that it contained about 30% of the Earth's total surface area. All the land that exists today on our planet was pressed together into this one enormous mass. Modern continents that now seem far apart were once neighbors on this ancient supercontinent. The northern part of Pangea included areas that would eventually become North America, Europe, and Northern Asia. Scientists sometimes call this northern section Laurasia, though that name more properly refers to a later period after Pangea began to break apart. The southern part of Pangea contained the future South America, Africa, Antarctica, Australia, and India. This southern region is often called Gondwana. The boundary between these northern and southern regions ran roughly along what would become the Mediterranean Sea and the Himalayan mountain ranges. But during Pangean times, this boundary was marked by the Central Pangean Mountains, that massive range we discussed earlier. These mountains created a significant barrier that influenced both climate and the movement of life forms across the supercontinent. The Tethys Sea played a crucial role in Pangea's geography and climate. This ancient ocean penetrated westward into the supercontinent for thousands of miles. At its widest point, the Tethys might have been 3,000 miles across. Its warm, shallow waters supported rich marine ecosystems and helped moderate the climate of nearby land areas. Building on this understanding of how Pangea assembled itself, we can now picture what this completed supercontinent actually looked like. Imagine looking down at Earth from space 250 million years ago. You would see something remarkable and strange. One enormous landmass surrounded by a vast, unbroken ocean. Pangea had a distinctive shape that scientists often describe as resembling the letter C. This wasn't a neat, compact circle of land, but rather a sprawling, curved continent that stretched from the North Pole all the way to the South Pole. The supercontinent was widest near the equator and narrower toward both poles. The eastern side of Pangea curved inward, creating a huge bay or gulf that penetrated deep into the supercontinent. Scientists call this ancient sea the Tethys Ocean. Picture a bite taken out of an apple, and you'll have some sense of how the Tethys Sea curved into Pangea's eastern shore. This wasn't just a small inlet, but a major oceanic feature that influenced climate and life across much of the supercontinent. The western shore of Pangea faced the vast world ocean that scientists call Panthalassa. This name comes from ancient Greek words meaning all ocean. Panthalassa covered roughly two-thirds of the Earth's surface. To put this in perspective, our modern Pacific Ocean is large, but Panthalassa was much larger. It stretched almost completely around the globe. If we could take a journey across Pangea from west to east, we would cover distances that seem almost impossible to imagine. The supercontinent measured roughly 10,000 miles from its western shore to its eastern shore. That's about 4 times the width of the United States. A journey from the northern tip of Pangea to its southern tip would cover even more ground, possibly 12,000 miles or more. To help visualize Pangea's size, consider that it contained about 30% of the Earth's total surface area. All the land that exists today on our planet was pressed together into this one enormous mass. Modern continents that now seem far apart were once neighbors on this ancient supercontinent. The northern part of Pangea included areas that would eventually become North America, Europe, and Northern Asia. Scientists sometimes call this northern section Laurasia, though that name more properly refers to a later period after Pangea began to break apart. The southern part of Pangea contained the future South America, Africa, Antarctica, Australia, and India. This southern region is often called Gondwana. The boundary between these northern and southern regions ran roughly along what would become the Mediterranean Sea and the Himalayan mountain ranges. But during Pangean times, this boundary was marked by the Central Pangean Mountains, that massive range we discussed earlier. These mountains created a significant barrier that influenced both climate and the movement of life forms across the supercontinent. The Tethys Sea played a crucial role in Pangea's geography and climate. This ancient ocean penetrated westward into the supercontinent for thousands of miles. At its widest point, the Tethys might have been 3,000 miles across. Its warm, shallow waters supported rich marine ecosystems and helped moderate the climate of nearby land areas. The coastline where the Tethys Sea met Pangea was probably quite complex, with many bays, peninsulas, and island chains. These coastal regions would have been among the most pleasant places to live on the supercontinent. The nearby ocean provided moisture for rainfall and helped moderate temperature extremes. Many of Pangea's most diverse ecosystems probably flourished in these coastal areas. Meanwhile, the interior of Pangea faced very different conditions. Areas that were more than 1,000 miles from any ocean experienced what scientists call a continental climate. This means hot summers, cold winters, and very little rainfall. Much of central Pangea was probably desert or semi desert, with only the hardiest plants and animals able to survive. The sheer scale of Pangea created geographic features that have no modern equivalent. Consider that the center of the supercontinent was roughly 3,000 miles from the nearest ocean in any direction. Today, no place on Earth is more than about 1,500 miles from the sea. This extreme continentality created climatic conditions unlike anything we see in our modern world. Scientists think Pangea's north-south orientation had important climatic consequences because the supercontinent stretched from pole to pole. It experienced the full range of Earth's climate zones. There were tropical regions near the equator, temperate zones in the middle latitudes, and polar conditions at both ends. This arrangement allowed for interesting patterns of seasonal change and animal migration. The position of Pangea on the globe also mattered. During its early existence, the supercontinent was rotated somewhat compared to today's land masses. Areas that are now in the northern hemisphere were closer to the equator than they are today. This meant that much of what would become North America and Europe experienced tropical or subtropical climates during Pangean times. As we imagine standing on the shores of ancient Pangea, we might wonder about the views our hypothetical observer would see. Looking west from the eastern coast, they would see the Tethys Sea stretching to the horizon. The water might be a brilliant tropical blue, with coral reefs and marine life quite different from anything in modern oceans. Looking east from Pangea's western shore, our observer would face Panthalassa, the world ocean. This view would be even more impressive than looking across today's Pacific. The horizon would seem to extend forever, with no hint of distant lands. Panthalassa was so vast that it contained island chains and underwater mountain ranges that we can only imagine. The complexity of Pangea's coastline created many different types of marine environments. There were probably deep oceanic areas, shallow continental shelves, tropical lagoons, and cooler temperate seas. Each of these environments supported different types of marine life, creating a rich diversity of oceanic ecosystems around the supercontinent's margins. Rivers on Pangea followed patterns quite different from those we see today. Some rivers probably flowed for thousands of miles across the supercontinent's interior before reaching the sea. The longest rivers might have been comparable to combining several of today's major river systems into single, enormous waterways. These rivers would have been crucial corridors for both water and life across the vast continental interior. The mountain ranges of Pangea also created interesting drainage patterns. The Central Pangean Mountains acted like a continental divide, separating rivers that flowed toward the Tethys Sea from those that flowed toward Panthalassa. During times of heavy rainfall, these rivers would have carried enormous amounts of sediment from the eroding mountains to the surrounding seas. Perhaps most remarkably, Pangea represented a unique moment in Earth's history when nearly all land was connected. This meant that land-dwelling creatures could potentially travel from what is now Alaska to what is now South Africa without crossing any significant body of water. Such connectivity had profound implications for the evolution and distribution of life forms. The unified nature of Pangea also simplified global ocean circulation in ways that are difficult to imagine today. Instead of the complex patterns of currents we see in our modern world. With its many separate ocean basins, Pangean oceans followed simpler patterns. This simplicity had far reaching effects on global climate and marine ecosystems. As we try to envision this ancient world, it's worth remembering that Pangea wasn't static. Even while it existed as a unified supercontinent, its climate, geography, and life forms continued to evolve. Rivers changed their courses, mountain ranges slowly eroded, and sea levels rose and fell. The Pangea of 280 million years ago was quite different from the Pangea of 200 million years ago. The distinctive sea shape of Pangea created unique opportunities for both ocean currents and atmospheric circulation. The large embayment of the Tethys Sea allowed ocean waters to penetrate deep into what would otherwise have been a solid continental mass. This created patterns of heating and cooling that influenced weather across much of the supercontinent. Over the millions of years of Pangea's existence, the supercontinent's relationship with the surrounding oceans slowly changed. Sea levels rose and fell, alternately flooding and exposing vast areas of coastal land. These changes created new environments and challenges for the life forms that called Pangea home. This leads us to consider the towering mountain ranges that dominated Pangea's landscape and helped shape its climate in ways that continue to influence our planet today. Rising from the heart of the supercontinent stood a mountain range that may have been among the tallest in Earth's history. Scientists call these the Central Pangean Mountains, and they dominated the geography and climate of the ancient world in ways we can barely imagine today. These mountains formed during the great continental collisions that assembled Pangea, when Gondwana and Euramerica pressed against each other over millions of years. The tremendous forces involved pushed vast areas of the Earth's crust upward. Rock layers that had once been seafloor were folded and lifted to create towering peaks. The process was slow but irresistible, building mountains grain by grain, year by year. Scientists believe the Central Pangean Mountains may have reached heights comparable to today's Himalayas. Some peaks possibly soared 6 kilometers or more above sea level. Picture a mountain range stretching for thousands of miles across the center of Pangea, with snow-capped peaks visible from hundreds of miles away. These mountains created a barrier that influenced everything from weather patterns to the movement of animals across the supercontinent. The formation of such massive mountains involved incredible geological processes. As the continental plates collided, layers of rock were compressed and folded like rumpled cloth. Some rock formations were pushed on top of others, creating complex geological structures. Ancient seafloor sediments, complete with marine fossils, were lifted far above sea level. Today, we can find fossils of sea creatures in high mountain peaks, evidence of this ancient mountain building process. The Central Pangean Mountains didn't rise uniformly across their entire length. Different sections experienced different amounts of uplift and erosion. Some areas developed into towering peaks, while others became rolling highlands. The complexity of the mountain system created diverse environments and climates across the range. Valleys between peaks became isolated worlds where unique plants and animals evolved. These ancient mountains had a profound influence on Pangea's climate. Like modern mountain ranges, they created rain shadows on their leeward sides. Moist air rising over the mountains would cool and drop its moisture as rain or snow on the windward slopes. The air that descended on the opposite side was dry, creating arid conditions in the lee of the peaks. This pattern helped create some of the vast deserts that characterized much of Pangea's interior. The mountains also affected global wind patterns in ways that are difficult to fully understand today. The Central Pangean Mountains were so extensive that they possibly altered the circulation of the atmosphere across much of the planet. These changes influenced seasonal patterns, temperature distributions, and rainfall across vast areas of the supercontinent and surrounding oceans. Over the millions of years that followed their formation, these mountains began the slow process of erosion. Rain, ice, and wind gradually wore away at the towering peaks. Rivers carved deep valleys through the mountain slopes, carrying sediment toward distant seas. The process was incredibly slow by human standards, but relentless over geological time. Mountains that had taken millions of years to rise were gradually worn down over equally long periods. Interestingly, we can still see remnants of the Central Pangean Mountains in our modern world. When Pangea eventually broke apart, different sections of this ancient mountain range ended up on different continents. The Appalachian Mountains of eastern North America are part of this ancient system. So are the Scottish Highlands, the mountains of Norway, and parts of the Atlas Mountains in North Africa. This geographic distribution provides compelling evidence for the existence of Pangea. Rock formations in the Appalachian Mountains match closely with rocks found in Scotland and Norway. The types of minerals, the ages of the rocks, and even the patterns of geological structures are remarkably similar. It's as if someone took a single mountain range and scattered its pieces across the Atlantic Ocean. Of course, that's essentially what happened when Pangea broke apart. The Caledonian Mountains of Scotland and Scandinavia represent another piece of this ancient puzzle. These hills and mountains, though much lower today than they once were, share geological characteristics with mountains on the other side of the Atlantic. Scientists can match rock layers and mineral deposits across these vast distances, providing strong evidence that these areas were once joined together in a single mountain system. The Atlas Mountains of Morocco and Algeria also carry traces of Pangean mountain building events. While these mountains have been modified by more recent geological processes, their foundations include rocks that were formed during the assembly of the supercontinent. The geological signatures locked in these rocks tell stories of ancient collisions and mountain building episodes that occurred hundreds of millions of years ago. Perhaps most remarkably, even the Ural Mountains of Russia represent a remnant of Pangean mountain building. These mountains mark the boundary between what we now call Europe and Asia, but during Pangean times, they represented the suture where the continent of Siberia collided with the growing supercontinent. The Urals are much lower today than they once were, worn down by millions of years of erosion, but they still stand as monuments to these ancient continental collisions. The process of mountain erosion during Pangean times had effects that extended far beyond the mountain ranges themselves. The sediments eroded from these peaks were carried by rivers to the surrounding seas. These sediments accumulated in thick layers on the ocean floor, eventually becoming the sandstones, shales, and other sedimentary rocks that we find today in many parts of the world. Some of the world's most important mineral deposits were formed in association with the Central Pangean Mountains. The geological processes that built these mountains also concentrated valuable ores and minerals. Gold, silver, copper, and other metals were concentrated in veins and deposits within the mountain rocks. Many of the mineral resources we depend on today have their origins in these ancient mountain building events. The mountains also influenced the development of coal deposits during Pangean times. The highlands created by mountain building provided sources of sediment that helped bury the great forests of the Carboniferous period. These buried forests eventually became coal deposits, many of which we still mine today. The relationship between mountain building and coal formation illustrates how geological processes are interconnected across vast scales of space and time. Climate zones around the Central Pangean Mountains were quite diverse. The high elevations supported cooler climates, possibly even glaciers during certain periods. Alpine meadows and cool forests may have flourished on mountain slopes, while warmer conditions prevailed at lower elevations. This diversity of climate zones within a relatively small geographic area supported rich ecosystems and encouraged the evolution of diverse plant and animal communities. The mountains also created important corridors and barriers for the movement of life forms across Pangea. Some species could migrate along mountain valleys, following favorable climates to new areas. Others found their movements blocked by high peaks or changed climate patterns. These geographic influences helped shape the evolution and distribution of life during Pangean times. Rivers flowing from the Central Pangean Mountains carried more than just sediment to the seas. They also transported nutrients that supported marine ecosystems around the supercontinent's margins. The weathering of mountain rocks released minerals that were essential for marine plants and animals. This connection between mountain erosion and marine productivity illustrates the complex interconnections within Earth's natural systems. The seasonal patterns of snow and ice accumulation on these ancient mountains probably influenced river flow patterns across much of Pangea. Spring melting of mountain snows would have created seasonal floods in rivers flowing away from the peaks. These flood cycles would have been important for both terrestrial and marine ecosystems, bringing fresh water and nutrients to areas that might otherwise have been quite dry. As we imagine these towering ancient peaks, it's worth remembering that they represented just one component of Pangea's complex landscape. The mountains interacted with the supercontinent's vast deserts, its coastal regions, and its inland seas to create a world of remarkable diversity. Despite being united in a single landmass, Pangea contained almost every type of environment that exists on Earth today. The legacy of the Central Pangean Mountains extends far beyond their physical remnants. The geological processes that built these peaks helped establish patterns of crustal structure that continue to influence our planet today. The roots of these ancient mountains, buried deep in the Earth's crust, still affect local geology and continue to influence the modern landscape in subtle ways. Over the centuries that followed their peak development, these magnificent mountains witnessed the rise and fall of countless ecosystems. They saw the evolution of new species and the extinction of others. They experienced ice ages and warm periods, wet climates and dry ones. Through it all, they stood as constant features of the Pangean landscape, slowly changing but enduring across geological time spans that challenge our imagination. Gradually, scientists began to notice that these mountains were part of an even larger story about how oceans and continents shaped the ancient world, leading us to explore the vast waters that surrounded and penetrated the supercontinent. While the supercontinent covered about 1/3 of Earth's surface, the remaining 2/3 was ocean. But this wasn't the complex system of separate seas that we know today. Instead, Pangea was surrounded and penetrated by waters that were both simpler and more vast than anything in our modern world. The greatest of these ancient waters was Panthalassa, whose name means all ocean in ancient Greek. Imagine an ocean so large that it wrapped almost completely around the planet. Panthalassa covered roughly 70% of the Earth's surface during Pangean times. To put this in perspective, our modern Pacific Ocean, vast as it is, would have been just a small portion of ancient Panthalassa. Standing on Pangea's western shore, an observer would have gazed out at water that extended for thousands of miles without interruption. There were no other major land masses visible across this ocean. No island continents broke the horizon. The water simply stretched endlessly toward the curve of the earth, creating views that dwarf even our most spectacular modern seascapes. Panthalassa was deep as well as wide. In some places, this ancient ocean possibly reached depths of 9 kilometers or more. The ocean floor contained underwater mountain ranges, deep trenches, and vast abyssal plains that remained hidden beneath miles of water. Volcanic islands occasionally rose from these depths, creating temporary stepping stones across the otherwise unbroken ocean surface. The circulation patterns in Panthalassa were remarkably different from what we see in today's oceans. With only one major landmass to work around, ocean currents followed simpler, more predictable paths. Scientists think these currents probably moved in great circular patterns or gyres that carried warm water toward the poles and brought cooler water back toward the equator. These simplified current systems had important effects on global climate. Ocean currents today help distribute heat around the planet, moderating temperatures and creating the climate zones we're familiar with. In the Pangean world, with its simpler oceanic circulation, heat distribution was probably more straightforward, but also more extreme in some ways. The eastern side of Pangea presented a very different oceanic environment. Here, the great embayment of the Tethys Sea penetrated deep into the supercontinent. The Tethys was much smaller than Panthalassa, but it played a crucial role in Pangea's climate and geography. This ancient sea was positioned near the equator, where it received intense solar heating throughout the year. The Tethys Sea was probably quite warm, with tropical conditions prevailing across much of its extent. Scientists believe its waters may have been similar to those of the modern Caribbean or Red Sea, but on a much larger scale. The combination of warm temperatures, shallow depths in some areas, and restricted circulation created ideal conditions for coral reefs and other tropical marine ecosystems. The shape of the Tethys Sea influenced weather patterns across much of Pangea. As we'll explore later, this sea played a key role in driving the massive monsoon systems that dominated the supercontinent's climate. The seasonal heating and cooling of Tethys waters helped create atmospheric pressure differences that drove powerful seasonal winds across the land. Unlike our modern world, with its multiple ocean basins connected by narrow straits and channels, the Pangean oceanic system was remarkably unified. Water could flow freely around most of the supercontinent's perimeter. This created a kind of global circulation highway that connected tropical and polar regions more directly than is possible today. The marine life of these ancient oceans was quite different from what we see today. Many groups of sea creatures that dominate modern oceans hadn't yet evolved during Pangean times. Other groups that were common then have since become extinct. The seas teemed with life, but it was life that would seem alien to modern observers. Ancient coral reefs flourished in the warm waters of the Tethys Sea and other tropical areas. These reefs were built by corals that were related to, but different from modern reef building species. The reef ecosystems supported diverse communities of marine creatures, including many types of fish, mollusks, and other invertebrates that have no direct modern descendants. In the deeper waters of Panthalassa, large marine reptiles ruled the seas. These weren't dinosaurs, which were primarily land creatures, but specialized marine animals that had evolved from earlier reptilian ancestors. Some of these sea reptiles reached enormous sizes, possibly rivaling modern whales in their dimensions. They filled the ecological roles that marine mammals occupy in today's oceans. The chemistry of Pangean oceans was also different from modern seas. Scientists think the water may have contained different concentrations of dissolved minerals and gases. The levels of oxygen dissolved in seawater possibly varied from what we see today, influencing the types of life that could survive in different oceanic environments. Ocean temperatures during Pangean times were generally warmer than today, particularly in tropical regions. The absence of polar ice caps during much of the Pangean period meant that cold polar water didn't mix with warmer tropical water as much as it does today. This created more stable temperature zones in the oceans, with less seasonal variation in many areas. The tidal patterns in Pangean oceans were influenced by the same moon that affects our tides today, but the simplified geography created different tidal experiences. With fewer enclosed bays and complex coastlines, tidal ranges in the open ocean were probably more predictable. However, the funnel-like shape of the Tethys Sea may have created some areas with unusually large tidal ranges. Seasonal patterns in the Pangean oceans were strongly influenced by the supercontinent's monsoon systems. During certain seasons, vast amounts of fresh water from monsoon rains would flow into coastal areas, temporarily reducing the salinity of near-shore waters. These seasonal changes created unique ecological opportunities for both marine and terrestrial life. The interaction between land and sea was perhaps more pronounced during Pangean times than it is today. With most land concentrated in one enormous continent, the contrast between terrestrial and marine environments was starker. Coastal areas experienced the meeting of vast continental climates with equally vast oceanic influences, creating unique environmental conditions along Pangea's shorelines. Rivers flowing from Pangea's interior carried enormous amounts of sediment to the surrounding seas. The erosion of the Central Pangean Mountains and other highland areas provided a constant supply of minerals and nutrients to coastal marine ecosystems. This sediment also gradually built up extensive coastal plains and delta systems around the supercontinent's margins. The seasonal runoff from monsoon rains created periodic floods of fresh water and nutrients flowing into Pangean seas. These seasonal pulses of river water supported blooms of marine plankton, which form the base of complex oceanic food webs. The timing and intensity of these seasonal inputs were crucial for the reproductive cycles of many marine species. Deep ocean circulation in the Pangean world was driven by the same basic physical processes that drive modern ocean currents, but the simplified geography created different patterns. Dense, cold water formed in polar regions and sank to the ocean depths, then flowed toward the equator. This deep water eventually rose to the surface in tropical regions, carrying nutrients that supported marine ecosystems. The volcanic activity associated with the formation and eventual breakup of Pangea also influenced oceanic conditions. Underwater volcanic eruptions added heat, minerals, and gases to seawater. Some volcanic events may have temporarily altered ocean chemistry across large areas, creating challenges and opportunities for marine life. Island chains occasionally formed in Panthalassa as underwater volcanoes built up to reach the ocean surface. These islands provided stepping stones for the occasional exchange of terrestrial life forms between distant parts of Pangea, though such exchanges were probably rare. Most of these volcanic islands were temporary features that eventually sank back beneath the waves as volcanic activity shifted elsewhere. The boundaries between different water masses in Pangean oceans were probably quite distinct. Tropical waters, polar waters, and the waters of enclosed seas, like the Tethys, had different temperatures, salinities, and biological communities. These boundaries created important ecological zones that influenced the distribution of marine life across the ancient oceans. As we try to imagine these vast ancient seas, it's worth remembering that they were constantly changing over the millions of years of Pangea's existence. Sea levels rose and fell, ocean currents shifted their patterns, and marine ecosystems evolved and adapted to changing conditions. The Pangean oceans were not static features, but dynamic systems that played crucial roles in shaping the ancient world. The legacy of these ancient oceans can still be found in the geological record. Limestone formations that were built from ancient coral reefs, salt deposits left by evaporating seas, and fossil-rich rocks that preserve ancient marine life all provide windows into the oceanic world of Pangea. These geological clues help scientists reconstruct the conditions that existed in seas that vanished hundreds of millions of years ago. Moving forward in time, we'll discover how the rhythm of these ancient seas was influenced by something even more fundamental, the different pace of time itself during the Pangean era, when days were shorter and the very rotation of our planet followed a different schedule. During the age of Pangea, the fundamental rhythm of day and night followed a different pattern than what we experience today. Days were shorter then, lasting only about 22 to 23 hours instead of our modern 24-hour cycle. Time itself moved to a different beat in the ancient world. This difference might seem small at first glance. What does an hour or two matter across the span of a day? But when we consider that this pattern continued for millions of years, we begin to understand how profoundly different the Pangean world must have felt. Every sunrise came a little sooner. Every sunset arrived a little earlier. The rhythm of life itself was quicker, more hurried. The reason for these shorter days lies in the relationship between Earth and its moon. Our planet's rotation has been gradually slowing down over the billions of years since the moon formed. This process continues today, though so slowly that we don't notice it in our daily lives. Scientists can measure it with precise instruments, but the change amounts to only a few milliseconds per century. During Pangean times, however, Earth was spinning noticeably faster than it does today. The moon was also closer to Earth then, which created stronger tidal forces. These tidal forces act like a gentle brake on Earth's rotation, gradually slowing our planet's spin over geological timescales. The closer moon of the Pangean era created stronger braking effects than we experience today. Think about what these shorter days might have meant for the creatures living on Pangea. The daily temperature cycle would have been compressed into a shorter time frame. Sunrise and sunset came more frequently. Plants and animals that relied on daily rhythms would have experienced more frequent cycles of light and darkness. The very pace of life might have felt different. Scientists believe that many biological processes are closely tied to the length of the day. The internal clocks that govern when plants open their leaves, when animals become active, and when various biochemical processes occur in living organisms are all calibrated to the day-night cycle. In the Pangean world, these biological rhythms would have been synchronized to a 22 or 23-hour cycle instead of our familiar 24-hour pattern. The shorter days also affected weather patterns in ways that are difficult for us to fully comprehend. Daily heating and cooling cycles were compressed. The sun rose more frequently, creating more frequent cycles of thermal expansion and contraction in the atmosphere. This may have influenced wind patterns, cloud formation, and precipitation in subtle but important ways. Ocean tides during Pangean times were quite different from what we see today. The closer moon created stronger tidal forces, but these forces acted over shorter time periods because of Earth's faster rotation. Scientists think this combination may have created more frequent, but possibly more intense tidal cycles. Coastal areas would have experienced high and low tides on a different schedule than modern coastlines. For marine life, these tidal differences would have been significant. Many sea creatures time their feeding, breeding, and other activities to tidal cycles. The stronger, more frequent tides of the Pangean era would have created different rhythms for marine ecosystems. Intertidal zones, the areas between high and low tide, would have experienced more frequent cycles of exposure and submersion. The relationship between Earth's rotation and atmospheric circulation also worked differently during Pangean times. The faster rotation created stronger Coriolis effects, the forces that influence how air masses move around our planet. This may have made weather systems more intense in some ways, creating stronger spiral patterns in storms and more pronounced deflection of wind systems. Seasonal changes on Pangea still followed the same annual cycle that we experience today, since Earth's orbit around the Sun remained essentially the same. However, within each season, the daily rhythm was different. Spring days in the Pangean world contained more individual day-night cycles than modern spring days. Each season was packed with slightly more sunrises and sunsets. The aurora, those beautiful light displays that occur near Earth's magnetic poles, probably appeared differently during Pangean times as well. The stronger magnetic field interactions caused by faster rotation and the closer moon may have created more frequent or more intense auroral displays. These lights in the sky would have been among the few phenomena that ancient observers might have noticed as distinctly different from what we see today. Plants living during Pangean times had to adapt to the shorter daily cycles in interesting ways. The process of photosynthesis, which converts sunlight into energy, would have operated on a 22 to 23-hour cycle instead of our modern 24-hour pattern. Many plants also open and close their leaves or flowers in response to daily light cycles. These behaviors would have been synchronized to the quicker rhythm of Pangean days. Animals, too, would have adapted their behavior to the shorter days. Creatures that are active during daylight hours would have experienced slightly shorter periods of activity. Nocturnal animals would have had shorter nights for their activities. Migration patterns, feeding schedules, and reproductive cycles all would have been influenced by the different daily rhythm. The geological processes that shape Pangea were also influenced by the shorter days, though in more subtle ways. The daily heating and cooling of rock surfaces happened more frequently. Thermal expansion and contraction occurred on a shorter cycle. Over millions of years, these small differences in the daily rhythm of heating and cooling may have influenced how rocks weathered and eroded. Rivers and lakes on Pangea would have experienced daily temperature variations on a compressed time scale. The shorter days meant that water bodies had less time to heat up during daylight hours and less time to cool down during the night. This may have created different patterns of water circulation and different conditions for freshwater ecosystems. The atmospheric pressure variations that occur throughout each day would also have followed a different pattern during Pangean times. These daily pressure changes, though small, influence weather patterns and can affect how life forms experience their environment. The 22 to 23-hour pressure cycle of the Pangean world would have been subtly but consistently different from our modern experience. As we consider these shorter days, it's worth reflecting on how fundamental the daily cycle is to life on Earth. Almost every living thing, from the smallest bacteria to the largest trees, has internal rhythms that are synchronized to the day-night cycle. In the Pangean world, all of these biological clocks were set to a different rhythm than what we know today. The measurement of time itself would have been different for any hypothetical observers in the Pangean world. While the year remained the same length, Earth's orbit around the Sun was essentially unchanged. Each year contained more individual days. A Pangean year might have contained 395 or 400 individual day-night cycles instead of our modern 365. The moon's appearance in Pangean skies would have been noticeably different as well. Being closer to Earth, it would have appeared larger than the moon we see today. The lunar phases would have cycled through their patterns more frequently relative to the daily rhythm, creating a different relationship between daily and monthly cycles than what we experience. Solar eclipses during Pangean times would have been quite spectacular. The larger apparent size of the moon, combined with its closer proximity, would have created more dramatic solar eclipses. These events would have appeared more frequently and might have lasted longer, creating impressive celestial displays for any observers fortunate enough to witness them. The combination of faster rotation and stronger tidal forces also influenced the solid Earth itself. The planet's shape was slightly different, being somewhat more flattened at the poles due to the faster spinning motion. This subtle difference in Earth's shape would have influenced gravitational patterns and possibly affected atmospheric circulation in ways we're still trying to understand. Over the millions of years that Pangea existed, the gradual slowing of Earth's rotation continued. Days became imperceptibly longer as time passed. No individual creature would have noticed this change during its lifetime, but over many generations, the cumulative effect was significant. By the time Pangea began to break apart, days were measurably longer than they had been when the supercontinent first formed. This gradual lengthening of days represents one of the many ways that Earth was slowly but constantly changing throughout the Pangean era. While the supercontinent appeared stable and permanent to any creatures living on it, the planet beneath their feet was actually in constant subtle motion. The very rhythm of time was shifting, day by day, year by year. As we imagine life in this world of shorter days, we might wonder how different the experience of time would have felt. Would life have seemed more hurried, more compressed, or would creatures have simply adapted to the quicker rhythm without any sense of difference? These questions remind us that our modern experience of time meters, our 24-hour days, our familiar tidal patterns, our accustomed relationship with the moon are not permanent features of our planet, but rather snapshots of Earth in its current configuration. Over the centuries that followed, these temporal rhythms would interact with Pangea's unique geography to create weather patterns unlike anything our modern world has ever experienced, leading us to explore the great monsoon systems that dominated the supercontinent's climate. Scientists call it the Pangean Megamonsoon, and it was unlike any climate pattern that exists in our modern world. This was a seasonal wind system of extraordinary scale and power, driven by the immense size of the supercontinent itself. To understand the Pangean Megamonsoon, we first need to consider what creates monsoon weather patterns. Monsoons happen when large land masses and nearby oceans heat up and cool down at different rates throughout the year. During summer months, land heats up faster than water, creating areas of low atmospheric pressure over the continents. Air flows from the cooler, higher pressure areas over the oceans toward the warmer, lower pressure areas over land, bringing moisture and rain. In our modern world, we see monsoon systems in places like India and Southeast Asia. These regional monsoons affect millions of people and cover thousands of square miles. But the Pangean megamonsoon was far larger and more powerful than any monsoon system that exists today. It possibly influenced weather patterns across the entire supercontinent, creating seasonal changes on a scale that's difficult for us to imagine. The sheer size of Pangea created conditions perfect for an enormous monsoon system. Picture a continent that stretched from pole to pole, covering about 1/3 of the Earth's surface. During summer months, this vast landmass would have heated up dramatically, especially in its interior regions. The contrast between the hot continental interior and the cooler surrounding oceans would have been extreme. The Tethys Sea played a crucial role in driving the Pangean megamonsoon system. This warm, tropical sea penetrated deep into the eastern side of the supercontinent, creating a massive source of moisture. As the land heated up during summer months, air would rise from the hot continental interior, drawing moist air inland from the Tethys Sea. This process happened on a scale that dwarfs any modern weather system. Scientists believe the Pangean megamonsoon created seasonal wind patterns that covered most of the supercontinent. During summer months, moisture-laden winds would have blown from the Tethys Sea deep into Pangea's interior. These winds would have carried enormous amounts of water vapor, creating conditions for massive seasonal rainstorms across vast areas of the continent. The seasonal rains brought by the megamonsoon were probably intense beyond anything we see in modern monsoon regions. Computer models suggest that some areas might have received several feet of rainfall during the wettest months. Rivers that were dry for much of the year would have become raging torrents during monsoon season. Vast areas of normally arid landscape would have been transformed into temporary lakes and wetlands. But the seasonal changes didn't stop with the wet season. During winter months, the wind patterns would have reversed dramatically. Cool, dry air from the continental interior would have flowed outward toward the surrounding oceans. This would have created months of extremely dry conditions across much of Pangea's interior. The contrast between wet and dry seasons would have been far more extreme than what we experience in any modern climate. These seasonal extremes created unique challenges for life on Pangea. Plants and animals had to survive not just seasonal temperature changes, but also dramatic shifts between flood and drought conditions. Some areas that were underwater during monsoon season would have become desert-like during the dry months. Life forms that thrived during the wet season would have had to find ways to survive the long dry periods that followed. The Central Pangean Mountains played an important role in shaping the monsoon patterns, as moisture-laden air from the Tethys Sea moved inland. It would have encountered these towering mountain ranges. The mountains would have forced the air upward, cooling it and causing much of its moisture to fall as rain on the windward slopes. The areas beyond the mountains, in the rain shadow, would have remained much drier. This interaction between the monsoon winds and the mountain ranges created a complex pattern of wet and dry regions across Pangea. Some valleys nestled in the mountains might have remained relatively moist throughout the year, while nearby areas just beyond the peaks would have been extremely arid. This geographic complexity supported diverse ecosystems within relatively small areas. The seasonal flooding caused by monsoon rains would have been spectacular to witness. Rivers that were mere trickles during the dry season would have become mighty waterways during the monsoon months. These floods would have carved new channels, deposited vast amounts of sediment, and created temporary wetland ecosystems that supported unique communities of plants and animals. The Pangean Megamonsoon also influenced ocean circulation patterns around the supercontinent. The seasonal winds would have driven surface currents in the surrounding seas, creating complex patterns of warm and cold water movement. These oceanic changes would have influenced marine ecosystems and helped distribute heat around the planet in ways quite different from our modern ocean circulation. Scientists study the ancient monsoon system through several types of geological evidence. Sedimentary rocks formed during Pangean times show clear signs of seasonal flooding and drying. Some rock layers contain the remains of plants and animals that lived in wet conditions, while others show evidence of drought and aridity. These alternating layers tell the story of the ancient monsoon cycle. Coal deposits from the Pangean era also provide clues about the ancient climate. Many coal beds show evidence of having formed in swampy conditions during wet seasons, followed by periods of drying and burial during drier months. The thickness and composition of these coal layers help scientists understand how intense and regular the seasonal changes were. The megamonsoon system wasn't constant throughout Pangea's existence. As the supercontinent's shape changed over millions of years, the monsoon patterns probably evolved as well. When Pangea was first forming, the monsoon system might have been less developed. As the continent reached its maximum size and the Tethys Sea achieved its deepest penetration into the landmass, the monsoon system probably reached its peak intensity. The atmospheric circulation patterns created by the megamonsoon extended far beyond Pangea itself. The enormous seasonal changes in pressure and wind patterns over the supercontinent would have influenced weather patterns across the entire planet. Even areas far from Pangea would have experienced weather changes related to the great seasonal rhythms of the megamonsoon system. Temperature changes associated with the monsoon seasons would have been dramatic as well. During the wet season, cloud cover and evaporation from flooded areas would have kept temperatures somewhat moderated. But during the dry season, clear skies and dry air would have allowed temperatures to reach extreme levels, especially in Pangea's interior regions. The dust and particles carried by the seasonal winds would have been another remarkable feature of the megamonsoon system. During the dry season, powerful winds would have lifted enormous amounts of dust and sand from the arid interior regions. This airborne material would have been carried for thousands of miles, creating dust storms on a continental scale. Some scientists think the Pangean Megamonsoon may have been one of the most powerful weather systems in Earth's history. The combination of the supercontinent's enormous size, its unique shape, and the presence of the Tethys Sea created conditions that were perfect for generating extreme seasonal wind patterns. No modern landmass is large enough to create comparable monsoon conditions. The seasonal rhythms of the megamonsoon would have created migration corridors for animals across Pangea. During the wet season, temporary rivers and wetlands would have provided pathways for aquatic and semi-aquatic creatures to move across otherwise dry landscapes. During the dry season, these same areas would have been accessible to land animals that couldn't normally cross water barriers. Plant communities across Pangea would have been shaped by the extreme seasonal patterns of the megamonsoon. Trees and shrubs would have had to survive months of drought, followed by months of flooding. Some plants probably evolved strategies for storing water during the wet season to survive the dry months. Others might have completed their entire life cycles during the brief wet season. The erosion caused by seasonal monsoon floods was probably immense. Each year, the powerful seasonal rains would have carved new channels, moved massive amounts of sediment, and gradually reshaped the landscape. Over millions of years, this erosion would have worn down mountains, filled in valleys, and transported enormous amounts of material from Pangea's interior to the surrounding seas. Human observers, if they had existed during Pangean times, would have found the monsoon seasons both challenging and awe-inspiring. The arrival of the wet season would have brought welcome relief from months of drought, but also dangerous flooding and storms. The transition between seasons would have been dramatic, with relatively short periods of moderate weather between the extremes of wet and dry conditions. The Pangean Megamonsoon represents one of the clearest examples of how Earth's climate can create conditions that have no modern equivalent. By studying this ancient weather system, scientists gain insights into how climate patterns might change as continents continue to drift and new geographic arrangements emerge in the distant future. As we try to imagine the power and scale of the Pangean Megamonsoon, we begin to appreciate how the supercontinent's climate was dominated by extremes. The seasonal winds were just one aspect of a climate system that created some of the most challenging environmental conditions in Earth's history, leading us to explore the full range of climatic extremes that characterized life in the Pangean world. These extremes made life challenging and fascinating in equal measure. At the heart of Pangea was its vast interior. With no nearby oceans to provide moisture, this region was likely hot and dry for much of the year. Scientists think it was a desert or semi-desert for thousands of miles. The heat during summer could have been intense, while winters might have brought cold, even freezing, temperatures. Imagine walking across a land where the temperature changes wildly from day to night. The heat of the day could make the ground feel like an oven, yet by night, the air might turn chilly. These daily swings, known as temperature extremes, were common in Pangea's interior. Along the coasts, conditions were milder and wetter. Coastal regions near the Tethys Sea and Panthalassa experienced seasonal rains brought by the megamonsoon winds. These rains created cycles of wet and dry seasons lasting many months. River valleys and lowland areas flourished as life found ways to adapt to these rhythms. Farther south in Pangea, ice caps possibly existed during the Permian period. These ice masses covered parts of the supercontinent near the South Pole. Their presence shows that even in this ancient era, Earth had regions cold enough to hold permanent ice, creating a stark contrast with the hot interior deserts. Daily temperature swings were sometimes extreme. In deserts, temperatures might soar over 100 degrees Fahrenheit during the day and drop below freezing at night. Life had to adapt to survive these changes. Plants and animals evolved special abilities to cope with heat and cold, drought and sudden floods. Many plants likely developed thick skins or waxy coatings to reduce water loss. Some animals may have burrowed underground during the heat of the day or waited out the dry season in protected shelters. These strategies helped living things endure conditions that would seem harsh to most modern species. The seasonal wet and dry cycles shaped the landscape itself. Rivers swelled during monsoon rains, carving deep valleys and depositing rich sediments. In dry seasons, water levels dropped, leaving behind mud flats and salt pans. These changing environments created habitats that attracted a variety of life. Climate zones on Pangea were arranged from pole to equator, much like today, but with more extreme differences. The northern regions might have had temperate forests and grasslands, while the equatorial belt featured tropical environments with dense vegetation. The southern parts showed colder climates with glaciers and tundra. In some regions, soil moisture was a limiting factor for plant growth. Areas far from water sources remained barren or sparsely vegetated. In contrast, areas near rivers, lakes, or coasts were green and lush, supporting a diverse array of plants and animals. The hot, dry interiors sometimes experienced dust storms, powered by strong winds blowing across the deserts. These dust storms could have carried sand and soil particles over long distances, affecting distant ecosystems and even oceanic environments. The presence of ancient deserts and glaciers at the same time highlights the variety of environments on Pangea. This diversity created a complex mosaic of habitats, each with its own challenges and opportunities for life to thrive or struggle. Life's adaptations to these extremes are visible in the fossil record. Fossils show species that were specialized for dry environments and others that preferred wetter habitats. Some animals had thickened skin or scales, while plants grew in clumps to conserve water. These environmental challenges shaped evolutionary paths. Survival required flexibility and resilience. Species that adapted to the shifting conditions of Pangea became ancestors of plants and animals we recognize today. Understanding these climate extremes helps us appreciate the dynamic nature of Earth's past. Pangea was not a uniform land, but a continent of contrasts, with life constantly responding to its changing rhythms. As we look back on this ancient world, we see that Earth's climate has always been in flux. From the blazing deserts to the icy poles, the ancient supercontinent taught life how to endure extremes, shaping the course of evolution across millions of years. Moving ahead, we will explore the atmosphere that blanketed this world, the air that life breathed. What was it like to inhale the Pangean atmosphere with its different balance of gases and volcanic influences? The atmosphere that blanketed Pangea contained a mix of gases quite unlike what we breathe today. The air during Pangean times held much more carbon dioxide than our modern atmosphere. Scientists believe carbon dioxide levels were sometimes 5 to 10 times higher than what we experience today. This created a thick, warm blanket of gas that trapped heat close to Earth's surface. The greenhouse effect was much stronger then, contributing to the generally warmer global climate. What would it have felt like to breathe such air? The higher carbon dioxide levels might have made the atmosphere feel slightly thicker or heavier. Though not immediately dangerous to life, this gas-rich air would have created a different sensation with each breath. Plants, which use carbon dioxide for photosynthesis, likely thrived in this carbon-rich environment. Oxygen levels also varied throughout the Pangean period. During some periods, there was less oxygen in the air than we have today. During others, oxygen levels were higher. These changes affected how both plants and animals lived and evolved. Creatures needed to adapt their breathing and energy systems to work with different amounts of available oxygen. The sources of these atmospheric changes were varied and fascinating. Volcanic activity played a major role in shaping Pangea's air composition. When volcanoes erupted, they released enormous amounts of carbon dioxide, sulfur compounds, and other gases into the atmosphere. The assembly of Pangea itself involved significant volcanic activity as continents collided and mountain ranges formed. Large volcanic provinces, areas where massive eruptions occurred over long periods, pumped gases into the atmosphere for thousands of years at a time. These prolonged volcanic episodes could change atmospheric composition across the entire planet. The gases released during these events created long-lasting effects on climate and air quality. The weathering of rocks also influenced atmospheric composition. As the great mountain ranges of Pangea eroded, chemical reactions between rocks and rainwater consumed carbon dioxide from the atmosphere. This process helped balance some of the carbon dioxide released by volcanic activity, creating a natural cycle of atmospheric regulation. Plant life during Pangean times both responded to and influenced atmospheric composition. With more carbon dioxide available, many plants grew larger and faster than their modern counterparts might. Dense forests and widespread plant coverage helped remove some carbon dioxide from the air through photosynthesis, while also releasing oxygen back into the atmosphere. The greenhouse effect created by high carbon dioxide levels meant that temperatures were generally warmer across most of Pangea. Even polar regions experienced milder conditions than they do today. This warmth allowed life to flourish in areas that would be too cold for most creatures in our current world. The thick, warm atmosphere created a global hothouse effect. Seasonal changes in atmospheric conditions were probably quite noticeable. During the great monsoon seasons, increased plant growth would have consumed more carbon dioxide from the air. The massive seasonal rains would have also washed various atmospheric compounds out of the air, temporarily changing its composition over large areas of the supercontinent. The ocean-atmosphere interaction was different as well. The warm seas of the Pangean world released more water vapor into the atmosphere than today's cooler oceans. This increased humidity made the air feel moist and heavy in many regions. The combination of high carbon dioxide, variable oxygen, and increased water vapor created a unique atmospheric mixture. Dust and particles in the air were probably more common during certain periods. The vast interior deserts of Pangea generated enormous dust storms that could carry fine particles across great distances. Volcanic eruptions added ash and sulfur compounds to the air. These particles sometimes blocked sunlight and created colorful sunrises and sunsets. The atmospheric pressure may have been slightly different as well, with the changed composition of gases and the effects of faster planetary rotation. The weight and density of the atmosphere might have felt subtly different from what we experience today. These differences would have been most noticeable at high altitudes in the Great Mountain Ranges. Chemical reactions in the Pangean atmosphere created compounds that don't form as readily in our modern air. The interaction between volcanic gases, dust particles, and moisture created complex atmospheric chemistry. Some of these reactions may have produced compounds that gave the air distinctive scents or colors at certain times and places. The aurora displays in Pangean skies might have appeared different due to the changed atmospheric composition. Different gases in the upper atmosphere would have created different colors and patterns when interacting with charged particles from the sun. These light shows could have been more frequent or more vivid than what we see today. Breathing this ancient air would have required no special adaptation for most life forms. The differences, while significant scientifically, were not extreme enough to prevent life from thriving. However, the long-term effects of living in such an atmosphere shaped the evolution of breathing systems in both plants and animals. The relationship between atmospheric composition and climate was particularly important during this time. The high levels of greenhouse gases created feedback loops that reinforced warming trends. As temperatures rose, more water evaporated from the oceans, adding even more greenhouse effect. As ice caps melted, less sunlight was reflected back to space, creating additional warming. Understanding the Pangean atmosphere helps scientists study how atmospheric composition affects global climate. The ancient world provides a natural laboratory for understanding what happens when greenhouse gas levels change dramatically. These lessons are valuable for understanding both past and future climate changes on our planet. The gradual changes in atmospheric composition over millions of years were so slow that no individual creature would have noticed them during its lifetime. Yet over many generations, these changes influenced evolution, climate patterns, and the development of ecosystems across the supercontinent. Aircraft flying through Pangean skies, if they had existed, would have encountered different flight conditions. The changed atmospheric density and composition would have affected how aircraft engines worked and how wings generated lift. The atmospheric turbulence patterns would have been different as well, influenced by the altered temperature and humidity distributions. The scents and smells of the Pangean world were probably quite distinctive. Volcanic gases, different plant life, and unique atmospheric chemistry would have created odors that have no modern equivalent. Some areas might have smelled of sulfur from volcanic activity, while others carried the rich scents of unfamiliar plant communities thriving in the carbon-rich air. As we imagine breathing the air of this ancient world, we gain a deeper appreciation for how interconnected Earth's systems truly are. The atmosphere, oceans, land, and life all influenced each other in complex ways. Changes in one system created ripple effects that touched every aspect of the Pangean environment. The legacy of the Pangean atmosphere can still be found in the geological record. Ice cores, though not available from that ancient time, are replaced by other indicators. Chemical signatures in rocks, the composition of ancient soils, and the types of minerals that formed all provide clues about what the air was like millions of years ago. This different atmosphere supported a remarkable variety of life forms, each adapted to the unique conditions of their time. As we continue our exploration, we'll discover the fascinating creatures that called this ancient world home, breathing its thick, warm air under skies unlike any we see today. Building on this understanding of Pangea's unique atmosphere, we turn our attention to the remarkable life forms that evolved to thrive in this alien world, creatures that seem both familiar and strange when viewed through the lens of deep time. The creatures that called Pangea home were both familiar and strange, representing evolutionary experiments that played out over millions of years under very different conditions than we see today. The land animals of Pangea were dominated by a group scientists call therapsids. These were not quite mammals as we know them, but they weren't typical reptiles either. The rhapsids had characteristics that bridged the gap between reptiles and mammals. Some had hair or fur-like coverings. Others may have been warm-blooded, able to control their body temperature in ways that most reptiles cannot. Picture creatures that looked somewhat like a cross between a modern dog and a lizard. Some therapsids were as small as mice, while others grew to the size of large bears. They walked on four legs, but their legs were positioned more directly under their bodies than most reptiles. This gave them a more efficient way of moving across the landscape. Many therapsids had teeth that were specialized for different functions. Some had sharp teeth for cutting meat, others had flat teeth for grinding plants. This specialization shows that these ancient creatures had developed diverse ways of finding food and surviving in their challenging environment. The variety of their teeth tells us about the rich ecosystems they lived in. The dominant predators among the therapsids were impressive creatures. Some, like an Ostransphaea, were large meat eaters with powerful jaws and saber-like teeth. These predators roamed the landscapes of Pangea, hunting other therapsids and early reptiles. Despite their fearsome appearance, they were actually more closely related to our ancestors than to modern crocodiles or lizards. Plant-eating therapsids were equally diverse and fascinating. Creatures like moschops had barrel-shaped bodies and small heads adapted for processing large amounts of plant material. They lived in herds and migrated across the seasonal landscapes of Pangea, following the monsoon rains and the fresh vegetation that sprouted in their wake. Some therapsids developed fascinating adaptations to the extreme climate of Pangea. Creatures living in the hot interior regions may have had enlarged ears or other features to help them stay cool. Those in seasonal environments might have been able to slow their metabolism during dry periods, much like some modern desert animals do. As Pangea's story unfolded, another group of creatures began to appear and gradually gain importance. These were the archosaurs, the ancestors of dinosaurs, crocodiles, and birds. During the later periods of Pangea's existence, the first true dinosaurs made their appearance, though they were small and relatively uncommon compared to the dominant therapsids. The early dinosaurs of the late Pangean period were quite different from the giants that would later rule the earth. Creatures like Everraptor were small, agile animals about the size of a large dog. They had long tails, walked on two legs, and were probably quick hunters that caught small prey. These humble beginnings would eventually lead to some of the most spectacular creatures ever to walk the earth. Other early archosaurs experimented with different ways of living. Some were crocodile-like creatures that lived in and around the rivers and lakes that formed during monsoon seasons. Others were more land-based and competed with therapsids for territory and food. The diversity of these early archosaurs shows how life was constantly trying new approaches to survival. The oceans and seas of the Pangean world supported their own remarkable communities of life. In the warm waters of the Tethys Sea, coral reefs flourished, but these reefs were built by corals quite different from modern ones. The reef ecosystems supported diverse communities of marine creatures, many of which have no modern equivalents. Large marine reptiles ruled the ancient seas much as whales and dolphins do today. These creatures had evolved from land-dwelling reptiles that had returned to the water. Some were long-necked and fed on fish and squid-like creatures. Others were more dolphin-like in shape and may have been active predators that hunted in groups. The seas also contained creatures that seemed almost alien by modern standards. Ancient ammonoids, relatives of modern squid and octopus, swam through Pangean waters with their coiled shells. Some of these shells were enormous, larger than truck tires. These creatures were among the most intelligent invertebrates of their time. Plant life on Pangea faced unique challenges and developed remarkable solutions. The extreme seasonal changes meant that many plants had to survive months of drought, followed by months of flooding. Some developed extensive root systems that could reach deep underground water sources. Others evolved ways to store water in their stems or leaves. The forests of Pangea were dominated by conifers, relatives of modern pine and fir trees. These trees were well adapted to the seasonal climate, able to survive both the dry periods and the flooding rains of the megamonsoon. Some grew to enormous sizes, creating dense forests in areas where conditions were favorable. In the drier interior regions, plants developed different strategies. Some completed their entire life cycle during the brief wet season, growing from seed to maturity and reproducing in just a few months. Others remained dormant for most of the year, only becoming active when rains arrived. These adaptations allowed plant life to colonize even the harshest environments on the supercontinent. Ferns were particularly successful during Pangean times. Giant tree ferns created lush understories in the forests, taking advantage of the high carbon dioxide levels in the atmosphere. Some of these ferns grew as tall as modern trees, creating forest environments that would have seemed almost tropical even in temperate latitudes. The fossil evidence that tells us about Pangean life is both abundant and frustratingly incomplete. Fossils form only under special conditions, so we have a partial picture of what life was really like. Most of our knowledge comes from creatures that lived near water, where their remains were quickly buried and preserved. The process of fossilization has given us remarkable glimpses into daily life on Pangea. We have fossils of therapsids preserved in the middle of caring for their young, showing that some of these ancient creatures had complex parental behaviors. We have trackways that show how herds of plant eaters moved across the landscape during seasonal migrations. Some of the most exciting fossil discoveries come from sites where entire ecosystems were preserved together. These fossil assemblages show us how different creatures interacted with each other and with their environment. We can see predator prey relationships, understand which plants different animals ate, and get a sense of how communities of life functioned in the ancient world. The chemistry preserved in ancient bones and teeth tells us even more about Pangean life. Scientists can analyze these chemical signatures to understand what ancient creatures ate, how warm their body temperatures were, and even what the climate was like when they were alive. These chemical clues add depth to the picture painted by the fossil bones themselves. Coprolites, fossilized waste products, provide intimate details about ancient diets and ecosystems. These specimens show us exactly what creatures were eating and how they were processing their food. While perhaps not glamorous, these fossils are among the most informative about how ancient ecosystems actually functioned. The preservation of soft tissues in some Pangean fossils has revealed surprising details about ancient life. We have evidence of skin textures, muscle attachments, and even possible feathers or hair-like coverings on some creatures. These rare preserved soft tissues help bridge the gap between fossil bones and living animals. Trace fossils, the preserved evidence of ancient behavior, tell stories about how creatures lived their daily lives. We have burrows showing where animals sheltered during harsh weather, footprints revealing their gaits and speeds, and feeding traces showing how they obtained food. These behavioral fossils add a dynamic element to our understanding of the ancient world. The distribution of fossils across different continents provides strong evidence for Pangea's existence. Similar creatures are found in rocks of the same age on continents that are now separated by vast oceans. The famous Therapsid lystrosaurus example is found in Africa, Antarctica, and Asia, showing that these areas were once connected. As we examine the fossil record of Pangea, we see patterns of evolution that would be impossible in our modern fragmented world. Species could spread across vast distances without ocean barriers. This connectivity allowed for large-scale evolutionary experiments and the development of cosmopolitan species that lived across much of the supercontinent. The end of many Pangean species came not through gradual change, but through one of the most significant events in Earth's history. The stage was being set for what scientists call the Great Dying, an extinction event so severe that it would reshape life on Earth and mark the end of the Therapsid-dominated world. The remarkable creatures of Pangea show us that life is endlessly creative in finding ways to survive and thrive. From the mammal-like therapsids to the early dinosaurs, from giant marine reptiles to resilient plants, life on Pangea developed solutions to challenges that no longer exist in our modern world. The diversity and adaptability of Pangean life forms remind us that our current ecosystems, impressive as they are, represent just one snapshot in the long story of life on Earth. The alien world of Pangea was home to its own remarkable communities, each adapted to the unique conditions of their time and place. As we reflect on these ancient life forms, we begin to understand that the story of Pangea includes not just geography and climate, but also one of the most severe challenges that life on Earth has ever faced. This leads us to explore the greatest crisis in the supercontinent's history, an event that would forever change the course of evolution on our planet. Around 252 million years ago, near the end of what scientists call the Permian period, life on Earth faced its greatest challenge. This event, sometimes called the Great Dying, was the most severe extinction in our planet's history. Yet even this profound change unfolded gradually over thousands of years in Earth's patient way of transformation. The extinction event didn't happen suddenly, like a single catastrophe. Instead, it was a slow process that possibly took between 60,000 and 200,000 years to complete. During this time, ecosystems gradually changed and many species slowly disappeared. The therapsids that had dominated Pangea for millions of years found their world becoming increasingly difficult to survive in. Scientists believe the primary cause of this great change was volcanic activity on an enormous scale. In what is now Siberia, massive volcanic eruptions began that would continue for hundreds of thousands of years. These weren't ordinary volcanoes, but rather vast outpourings of lava that covered an area larger than modern Europe. The Siberian traps, as scientists call this volcanic province, released enormous amounts of gas and ash into the atmosphere. The volcanic emissions gradually changed the composition of both the atmosphere and the oceans. Carbon dioxide levels, already high during Pangean times, increased even further. The additional greenhouse gases warmed the planet beyond what many species could tolerate. Ocean chemistry changed as well, becoming more acidic and depleted in oxygen in many areas. These environmental changes created a cascade of effects that rippled through ecosystems across Pangea. Marine environments were particularly affected, with coral reefs disappearing and many sea creatures unable to adapt to the changing water chemistry. The warm, oxygen-poor seas could no longer support the diverse marine communities that had flourished during earlier Pangean times. On land, the changing climate and atmosphere created new challenges for the dominant therapsids. Many plant species disappeared, disrupting food chains that had been stable for millions of years. The seasonal monsoon patterns that had characterized Pangean climate may have become more extreme or unpredictable, making it harder for animals to time their migrations and breeding cycles. The extinction process was gradual enough that some species had time to adapt or migrate to more favorable areas. However, the changes were so widespread and persistent that even these adaptive strategies eventually failed for many creatures. The interconnected nature of ecosystems meant that the disappearance of some species created problems for others that depended on them. Different regions of Pangea experienced the extinction at different rates and intensities. Some areas may have served as refuges, where certain species survived longer than elsewhere. These pockets of survival were important for the eventual recovery of life, providing seed populations that could later spread and diversify when conditions improved. The marine extinction was particularly severe, with scientists estimating that about 90% of marine species disappeared during this time. Ancient coral reefs were almost completely eliminated, and many groups of marine creatures that had been common for millions of years vanished entirely. The vast oceans that surrounded Pangea became much simpler ecosystems with far fewer species than before. On land, the extinction was somewhat less severe, but still profound. Perhaps 70% of land-dwelling species disappeared during this period. Many of the large therapsids that had been the dominant land animals vanished. The diverse plant communities that had covered much of Pangea were reduced to much simpler assemblages of hardy, adaptable species. Yet life, as it always does, found ways to persist and eventually recover. Some therapsids survived in small populations and continued their lineages. More importantly for the future, some of the early archosaurs and other reptile groups weathered the extinction crisis better than their therapsid competitors. This set the stage for new evolutionary possibilities in the post extinction world. The recovery from the Great Dying was slow but steady. It possibly took millions of years for ecosystems to rebuild their complexity and diversity. During this recovery period, the survivors had opportunities to expand into ecological roles that had been left empty by extinct species. This process of ecological expansion and adaptation drove new evolutionary innovations. Some of the most interesting aspects of the recovery involved the rise of new types of organisms. The archosaurs, which had been relatively minor players during the height of therapsid dominance, began to diversify and occupy new ecological niches. This group would eventually give rise to dinosaurs, but during the immediate post extinction period, they remained relatively small and uncommon. Plant communities also slowly recovered, but with different compositions than before the extinction. Some plant groups that had been dominant disappeared entirely, while others that had been rare became more common. The changing plant communities created new opportunities and challenges for the herbivorous animals that depended on them. The ocean recovery was particularly gradual. It took millions of years for coral reefs to redevelop, and when they did, they were built by different types of corals than had existed before the extinction. Marine food webs slowly became more complex again, but with different species filling the various roles than had existed in the pre-extinction seas. The extinction event and its aftermath demonstrate the resilience of life on Earth. Despite the severity of the changes, life not only survived but eventually flourished again. The recovery period was a time of evolutionary experimentation, as surviving species adapted to new conditions and opportunities. Climate gradually stabilized as the volcanic emissions from Siberia decreased, and the atmosphere slowly returned to more normal compositions. Ocean chemistry gradually improved as well, allowing marine life to recover and diversify. The monsoon patterns that characterized Pangean climate may have also returned to more predictable patterns. The fossil record of this extinction and recovery provides valuable insights into how ecosystems respond to major environmental changes. Scientists study these ancient events to better understand how life adapts to changing conditions and how long recovery processes typically take. One of the remarkable aspects of the Great Dying was that it affected different groups of organisms in different ways. Some groups disappeared entirely, while others passed through the extinction with relatively little change. These differential effects shaped the evolutionary trajectory of life for millions of years afterward. The therapsids, despite being severely affected by the extinction, didn't disappear entirely. Some lineages survived and continued to evolve, eventually giving rise to the first true mammals many millions of years later. In this way, the extinction event, despite its severity, was not an ending, but rather a major transition in the story of life on Earth. The Great Dying also marked an important transition in Pangea's own history. The environmental stresses associated with the extinction may have been related to the geological processes that would eventually lead to the supercontinent's breakup. The massive volcanic activity in Siberia was possibly connected to the same deep earth processes that would later begin to pull Pangea apart. As we consider this great transition in the history of life on Pangea, we see both endings and beginnings. The world that emerged from the extinction was different from what had come before, but it was also full of new possibilities. The stage was being set for new chapters in the story of life, including the eventual rise of the dinosaurs and the slow transformation of Pangea itself. The recovery from the Great Dying reminds us that even the most severe challenges can become opportunities for renewal and change. Life's creativity and adaptability ensured that Earth's story would continue, leading to new evolutionary experiments and the gradual development of the ecosystems that would characterize the later periods of Pangean history. Over the centuries that followed this great transition, the survivors and their descendants slowly began to rebuild the complex web of life. Meanwhile, deep beneath their feet, other processes were beginning to stir that would eventually transform the very shape of their world, leading us to explore the first signs that Pangea itself was beginning to change. The first signs of change were subtle and would have been invisible to most observers. Deep within the Earth's crust, the same forces that had once pushed continents together were beginning to work in the opposite direction. The enormous weight and size of Pangea itself may have contributed to these changes, creating stresses in the underlying rock that would eventually find release. Scientists believe that one of the earliest signs of Pangea's future breakup was the formation of what they call rift valleys. These were long, narrow depressions in the Earth's surface where the crust was beginning to stretch and pull apart. At first, these rifts were probably small and isolated, scattered across different parts of the supercontinent like tiny cracks in an otherwise solid foundation. The development of these early rift systems was incredibly slow, proceeding at rates of perhaps a few millimeters per year. Over human lifespans, such changes would be completely unnoticeable. Even over the lifespans of the longest lived trees or animals, the movement would be imperceptible. Only when viewed across millions of years do these tiny increments of change become visible as major geological transformations. Some of the first clear signs of impending change appeared in what would eventually become the Central Atlantic Ocean. Here, the crust began to develop a series of parallel cracks and fault systems. These early fractures ran roughly north-south, following lines of weakness in the continental crust. The pattern of these fractures would eventually determine the shape of the ocean that would separate the Americas from Europe and Africa. Volcanic activity began to increase in certain regions of Pangea during the Triassic period. This wasn't the massive extinction-causing volcanism of the Siberian traps, but rather a more distributed pattern of volcanic eruptions. Many of these volcanoes were associated with the developing rift systems, as molten rock from deep in the earth found pathways to the surface through the newly forming cracks. The basaltic lava flows that erupted during this time created distinctive rock formations that geologists can still identify today. These ancient lava flows are found on both sides of the modern Atlantic Ocean, providing clear evidence that the areas which are now separated by thousands of miles of ocean were once adjacent parts of the same volcanic system. As the rift systems continued to develop, they began to connect with each other, forming longer and more continuous zones of weakness in the continental crust. Like cracks spreading slowly through glass, these rifts followed the path of least resistance through the supercontinent. The eventual pattern of breakup was being established, though it would take millions more years to complete. The formation of these rift systems created new types of environments on Pangea's surface. The rift valleys became natural drainage systems for rivers and streams. During the seasonal monsoons, these valleys would fill with water, creating long, narrow lakes. Some of these rift lakes persisted year-round, providing oases of permanent water in otherwise seasonal environments. These Rift Valley lakes became important habitats for both plants and animals. The permanent water supported fish and other aquatic creatures, while the lake shores provided favorable conditions for a variety of terrestrial species. Some of our best fossils from the Triassic period come from sediments that accumulated in these ancient rift lakes. The gradual stretching of the continental crust had other effects as well. As the crust was pulled apart, it became thinner in some areas. This thinning allowed heat from the Earth's interior to reach closer to the surface, creating warm springs in areas of geothermal activity. These warm spots may have provided refuges for life during cooler periods and could have influenced local climate patterns. The changing stress patterns in the continental crust also affected the existing mountain ranges on Pangea. The Great Central Pangean Mountains, which had been built by the collision forces that assembled the supercontinent, began to experience different types of forces as the crust started to pull apart. This led to new patterns of faulting and possibly contributed to increased erosion in some areas. Earthquake activity probably increased during this period as well, though the earthquakes would have been different from those we might experience today. Instead of the sudden sharp movements associated with modern earthquake zones, the early rifting process probably produced more frequent but gentler seismic activity as the crust slowly adjusted to the changing stresses. The sedimentary record from the Triassic period shows evidence of these changing conditions. Rock layers from this time often contain distinctive red sandstones and mudstones formed in the arid and semi-arid conditions that characterized much of Pangea's interior. The presence of salt deposits and evaporate minerals in some areas suggests that the developing rift valleys occasionally became closed basins where water would collect and evaporate. Paleomagnetic evidence locked in rocks from this period provides additional clues about the early stages of continental breakup. As volcanic rocks cooled and solidified, they preserved the orientation of the Earth's magnetic field at that time. By studying these magnetic signatures, scientists can track how different parts of Pangea were beginning to rotate and move relative to each other. The Davy-Hanna-spheric composition continued to change during this period as well. The increased volcanic activity associated with early rifting released additional carbon dioxide and other gases into the atmosphere. While not as extreme as during the Great Dying, these atmospheric changes may have contributed to continued warm conditions across much of the planet. Life forms during the Triassic period were largely unaware of these deep geological stirrings. The early dinosaurs that were beginning to diversify during this time lived their lives on what seemed to be solid, stable ground. The archosaurs that were becoming increasingly successful had no way of knowing that the world beneath their feet was slowly preparing for a major transformation. Plant communities also showed no immediate response to the early stages of continental rifting. The conifers, ferns, and other vegetation that had recovered from the Permian extinction continued to develop and spread across available habitats. Some plants may have even benefited from the new ecological niches created by Rift Valley lakes and streams. Marine life in the Tethys Sea and surrounding oceans also continued to recover and diversify without any apparent awareness of the changes happening on land. New types of marine reptiles evolved, coral reefs slowly reestablished themselves, and oceanic ecosystems gradually became more complex again after the simplification of the Great Dying. The processes that were beginning to transform Pangea during the Triassic period illustrate the patient, persistent nature of geological change. The forces that would eventually create new oceans and reshape continents were building gradually, following the Earth's characteristic pattern of slow but inevitable transformation. What seemed permanent and unchanging to contemporary life forms was actually the beginning of one of the most significant geographical changes in our planet's history. The evidence for these early stages of continental breakup is preserved in rocks that can be found today on multiple continents. The matching patterns of ancient rift systems, the similar ages and compositions of volcanic rocks, and the consistent paleomagnetic signatures all tell the story of a supercontinent beginning its long journey toward fragmentation. As we consider these early signs of change, we gain appreciation for the vast timescales over which Earth's major transformations occur. The breakup of Pangea would take tens of millions of years to complete, proceeding at rates so slow that individual generations of life forms would notice no change at all. Yet the cumulative effect of these tiny increments of movement would eventually reshape the entire surface of our planet. The Triassic period thus represents a crucial transition time in Earth's history. It was a period when life was recovering and diversifying after the Great Extinction, while simultaneously the stage was being set for the next major chapter in our planet's geological story. The signs of change were subtle but significant, marking the beginning of the end for the greatest supercontinent our planet has ever seen. In parallel to this slow preparation for change, the geological forces beneath Pangea continued to build toward the moment when the supercontinent would begin its dramatic transformation, leading us to witness the actual process of how a unified world became the separated continents we know today. The transition from early rifting to actual continental separation happened gradually, like the slow opening of a zipper that had held the world together. The rift valleys that had been forming during the Triassic period began to widen and deepen. What had once been narrow cracks in the continental crust became broader valleys, and these valleys slowly filled with water from the surrounding oceans. Scientists believe the breakup process began in earnest when the continental crust became stretched so thin that it could no longer support its own weight. At certain points along the developing rift systems, the crust actually broke through completely, allowing seawater to flow into the newly formed gaps. This marked the beginning of seafloor spreading, a process that would create entirely new ocean basins. The first areas to experience complete separation were probably located in what would become the Central Atlantic Ocean. Here, the rift systems that had been developing for millions of years finally succeeded in pulling the continental crust apart. Molten rock from deep within the Earth rose to fill the gap, creating new oceanic crust as it cooled and solidified. This process of seafloor spreading was different from anything that had happened during Pangea's formation. Instead of continents colliding and joining together, the Earth was now creating new crustal material and pushing existing continents apart. The seafloor spreading centers became like underwater mountain ranges, constantly producing new oceanic crust that pushed the continental margins farther and farther apart. The early Atlantic Ocean that formed between the separating continents was initially very narrow, perhaps only a few dozen miles wide. Picture a long, thin lake stretching north and south between what would become the Americas on one side and Europe and Africa on the other. This narrow seaway gradually widened as the seafloor spreading process continued, adding new oceanic crust at a rate of perhaps an inch or two per year. The breakup of Pangea proceeded in stages, with different parts of the supercontinent separating at different times. The first major division created two large land masses that scientists call Laurasia in the north and Gondwana in the south. Laurasia included what would become North America, Europe, and much of Asia, while Gondwana contained the future South America, Africa, Antarctica, Australia, and India. The separation between Laurasia and Gondwana was marked by the expansion of the Tethys Sea, which began to spread westward as the continents pulled apart. This expanding seaway created a more complex geography than had existed during Pangea's unified period. For the first time in over 100 million years, there were multiple large landmasses separated by significant bodies of water. Life forms during this period experienced the breakup process as a very gradual change in their environment. The opening of new seaways happened so slowly that individual organisms would have noticed no change during their lifetimes. Even entire species could evolve, thrive, and become extinct without experiencing any obvious effects from the continental separation that was occurring beneath them. However, over longer time periods, the effects of continental breakup became significant for evolution and ecology. Populations of plants and animals that had once been connected across Pangea's unified landmass became separated by growing ocean barriers. This isolation allowed different evolutionary experiments to occur on the separating continents, leading to increased diversity in the global biosphere. The volcanic activity associated with seafloor spreading created new types of environments along the continental margins. Coastal areas near the spreading centers experienced frequent earthquakes and volcanic eruptions as the crust adjusted to the ongoing separation. These geologically active zones became important areas for the formation of mineral deposits and unique ecological communities. The climate patterns that had characterized unified Pangea also began to change as the supercontinent broke apart. The enormous seasonal monsoon systems that had dominated Pangean weather started to weaken as the land masses became smaller and more separated. Ocean currents, which had been relatively simple during the supercontinent period, began to develop more complex patterns as new seaways opened and existing ones expanded. The Central Pangean Mountains, which had been built during the supercontinent's assembly, found themselves in a very different tectonic environment as breakup proceeded. Instead of being compressed by continental collisions, these ancient mountain ranges now experienced stretching forces that gradually pulled them apart. This led to new patterns of faulting and erosion that would shape their development for millions of years to come. The early stages of continental breakup also affected the global sea level, as new oceanic crust was created at seafloor spreading centers. It displaced seawater and caused global sea levels to rise gradually. This rise in sea level flooded low-lying areas of the separating continents, creating shallow inland seas and continental shelves that provided new habitats for marine life. The chemistry of the oceans also changed during this period. The volcanic activity associated with seafloor spreading released various gases and minerals into seawater, altering its composition. The increased surface area of oceanic crust provided more opportunities for chemical interactions between seawater and rock, leading to changes in ocean chemistry that affected marine ecosystems. Different parts of Pangea experience the breakup process in different ways. Some areas pulled apart relatively cleanly, creating simple rift valleys that eventually became ocean basins. Other areas experienced more complex patterns of separation, with multiple rift systems developing simultaneously and sometimes competing with each other for dominance. The separation was not always a smooth, continuous process. Sometimes the spreading would slow down or even stop temporarily before resuming. Occasionally, the direction of spreading would change slightly, creating bends and offsets in the developing ocean basins. These variations in the breakup process created the complex patterns of continental margins that we can observe today. As the continental separation continued, the narrow seaways that initially formed between the land masses gradually widened into recognizable ocean basins. The early Atlantic Ocean, which had started as a thin crack between continents, slowly grew wider and deeper. Similar processes were beginning to occur in other parts of the former supercontinent, setting the stage for the eventual creation of the Indian and Southern Oceans. The breakup process created new opportunities for the evolution of marine life. The expanding ocean basins provided vast new habitats for oceanic species, while the complex coastlines created by continental separation offered diverse environments for coastal and shallow water communities. The isolation of different ocean basins also allowed marine life to evolve along different pathways in different parts of the world. Land life also began to diversify in response to continental separation. As populations became isolated on different land masses, they evolved in different directions, leading to increased biological diversity across the separating continents. This process of diversification through geographic isolation would become one of the most important drivers of evolution during the post-Pangean world. The dinosaurs, which were becoming increasingly diverse and successful during this period, spread across the separating continents while they were still connected by land bridges. However, as these connections were gradually severed by rising sea levels and continued continental drift, dinosaur populations on different continents began to evolve in different directions. Plant life also responded to the changing geography of the breaking supercontinent. The modification of climate patterns as Pangea broke apart created new environmental conditions that favored different types of vegetation. The opening of new seaways allowed for new patterns of seed and pollen dispersal, facilitating the spread of plant species across the developing ocean barriers. The breakup process was accompanied by significant volcanic activity, not only at the seafloor spreading centers, but also in continental areas. Large igneous provinces formed in several parts of the separating supercontinent, creating vast areas of volcanic rock that can still be identified today. This volcanic activity may have influenced global climate through the release of gases into the atmosphere. The magnetic signatures preserved in the oceanic crust created during this period provide scientists with detailed records of the breakup process. As new oceanic crust formed its spreading centers, it recorded the orientation of Earth's magnetic field at the time of its formation. These magnetic stripes, preserved in the seafloor, allow scientists to track the rate and direction of continental separation with remarkable precision. The sedimentary record from this period shows evidence of the changing environments created by continental breakup. Rock layers formed during the early stages of separation often contain distinctive fossils and mineral assemblages that reflect the transition from continental to marine conditions. These sedimentary sequences provide detailed histories of how specific regions experienced the transformation from unified supercontinent to separated continents. As we consider this great unzipping of the world, we see how the Earth's surface can be completely transformed over geological timescales. The process that began with tiny cracks in the continental crust eventually led to the creation of entire ocean basins and the geographic arrangement that characterizes our modern world. The breakup of Pangea demonstrates both the power of geological forces and the incredible patience with which they operate, creating transformations so gradual that they are invisible to individual observers, but so profound that they reshape the entire planet. The legacy of Pangea's breakup continues to influence our world today, as the continents continue their slow drift across Earth's surface, carried by the same processes that first pulled the great supercontinent apart millions of years ago. Moving forward in time, we explore how scientists have pieced together this remarkable story of ancient unity and gradual separation, using clues locked away in rocks, fossils, and the very structure of our modern continents. The first clues came from something quite simple that anyone can observe. If you look at a map of the world, you might notice that the coastlines of different continents seem to fit together like pieces of a puzzle. The eastern coast of South America appears to match the western coast of Africa. The bulge of Brazil looks like it could nestle perfectly into the curve of West Africa's coastline. This observation, which seems so obvious once pointed out, was one of the earliest hints that continents might once have been joined together, but coastlines alone couldn't prove that Pangea had existed. Scientists needed more substantial evidence, and they found it by studying the rocks themselves. When geologists began examining rock formations on different continents, they discovered something remarkable. Rock layers of the same age and composition could be found on opposite sides of the Atlantic Ocean. The Appalachian Mountains of North America contained rocks that were virtually identical to rocks found in Scotland and Norway. The similarities weren't just general both. They were specific and detailed. These matching rock formations told a compelling story. The types of minerals, the patterns of layering, and even the sequences of different rock types were so similar that they seemed to be parts of the same original formation. It was as if someone had taken a single mountain range and moved pieces of it to different continents, thousands of miles apart. The evidence became even more convincing when scientists studied the internal structure of these rock formations. The way the rock layers were folded, the directions of ancient fault lines, and the patterns of mineral veins all matched across the oceans. These structural features formed during the original mountain building processes that created Pangea, and they preserved the memory of those ancient events. Pill deposits provided another type of geological evidence for Pangea's existence. Scientists found coal beds of the same age and similar composition on continents that are now widely separated. The coal deposits in eastern North America matched those in Western Europe. Similar coal formations were found in parts of South America, Africa, India, and Australia. What made this evidence particularly compelling was the specific types of plant fossils found in these coal deposits. The same species of ancient plants appeared in coal beds on different continents, suggesting that these areas had once shared the same climate and been connected by land. Modern plants couldn't have spread their seeds across thousands of miles of ocean, so these fossils indicated that the continents must have been joined when the plants were alive. Glacial evidence provided yet another piece of the Pangea puzzle. Scientists found signs of ancient ice ages in places that seemed impossible for glaciers to have existed. Scratches and grooves carved by moving ice were discovered in rocks in tropical Africa, South America, India. The patterns of these glacial markings all pointed in directions that made sense only if the continents had once been arranged differently. When scientists reconstructed Pangea's geography, these puzzling glacial features suddenly made perfect sense. The areas that showed evidence of ancient glaciation had all been located near the South Pole when Pangea existed. The ice sheets that had carved the mysterious grooves were part of a large polar ice cap that covered the southern part of the supercontinent. Fossil evidence became perhaps the most convincing proof of Pangea's existence. Scientists discovered identical fossils of land animals and plants on continents separated by vast oceans. The famous therapsid Lystrosaurus was found in rocks of the same age in South Africa, Antarctica, and India. This plant-eating creature couldn't have swum across oceans, yet its fossils appeared on multiple continents. The fossil evidence wasn't limited to land creatures. Scientists found fossils of freshwater reptiles like Mesosaurus in both South America and Africa. These animals lived in lakes and rivers, not in salt water, so they couldn't have crossed oceans. Their presence on different continents provided strong evidence that these land masses had once been connected by freshwater systems. Plant fossils told similar stories. Jacede fern Glossopteris was found in rocks of the same age across the southern continents, South America, Africa, Antarctica, Australia, and India. This plant produced seeds that were too heavy to be carried by wind across oceans, yet its fossils appeared on all the southern land masses. The only reasonable explanation was that these continents had once been joined. Perhaps the most sophisticated evidence for Pangea came from studying the magnetic properties of ancient rocks. When certain types of rock form, they lock in the direction of Earth's magnetic field at the time of their formation. By studying these paleomagnetic signatures, scientists could determine not only that continents had moved, but also how far they had traveled and in which directions. The paleomagnetic evidence showed that rocks now found in North America had formed at latitudes much closer to the equator. Similarly, rocks in other parts of the world had formed at different latitudes than where they are found today. This evidence provided quantitative proof that continents had indeed drifted across the Earth's surface over geological time. The magnetic patterns preserved in the seafloor provided additional confirmation of continental drift. As new oceanic crust formed at mid-ocean ridges, it recorded the orientation of Earth's magnetic field. The resulting pattern of magnetic stripes on the seafloor showed exactly how the ocean basins had opened as Pangea broke apart. Scientists also found evidence of Pangea in the distribution of mountain ranges and geological structures. The Caledonian Mountains, which include the Scottish Highlands and parts of Norway, could be traced across the North Atlantic to the Appalachian Mountains of North America. When the continents were fitted back together in the Pangea configuration, these mountain ranges lined up perfectly as parts of a single continuous range. The detective work of geology required scientists to think like puzzle solvers, fitting together pieces of evidence from around the world. Each type of evidence, the matching rocks, the identical fossils, the paleomagnetic signatures, the glacial features, told part of the story. When all the evidence was combined, it painted a clear picture of a supercontinent that had existed in the distant past. The process of reconstructing Pangea was gradual and required the work of many scientists over several decades. Early researchers, like Alfred Wegener, proposed the basic idea, but they lacked a mechanism to explain how continents could move. It wasn't until the discovery of plate tectonics in the 1960s that scientists understood the forces that could move continents across the Earth's surface. Modern technology has allowed scientists to refine their understanding of Pangea with increasing precision. Satellite measurements can track the current movement of continents with millimeter accuracy. Computer models can simulate the forces that drove continental drift in the past. Age dating techniques can determine exactly when different parts of Pangea separated. The evidence for Pangea is now so overwhelming that the supercontinent's existence is accepted as scientific fact. The same types of evidence continue to be discovered as scientists explore new areas and develop new techniques for studying ancient rocks. Each new piece of evidence adds detail to our understanding of what the Pangean world was like. The geological detective work that revealed Pangea demonstrates the power of scientific inquiry to uncover Earth's hidden history. By carefully observing, measuring, and comparing evidence from around the world, geologists have been able to reconstruct events that happened hundreds of millions of years ago. The rocks themselves serve as archives, preserving the story of our planet's past in forms that can be read by those who know how to interpret them. This detective work continues today as scientists search for evidence of even older supercontinents that may have existed before Pangea. The same methods that revealed Pangea's existence are being used to explore Earth's even more ancient history, pushing our understanding further and further back into the depths of geological time. The story preserved in stone reminds us that our planet has a rich and complex history that extends far beyond human experience. The continents beneath our feet have traveled great distances, experienced dramatic climate changes, and been home to countless forms of life that have long since vanished. Yet their stories survive, written in the language of rock and fossil, waiting for patient scientists to decode their messages. As we consider the remarkable detective work that revealed Pangea's existence, we gain appreciation for both the ingenuity of scientific investigation and the incredible archive of information preserved in Earth's geological record. The echoes of ancient worlds speak to us through stone, telling stories of unity and separation, of life and extinction, of change and continuity across the vast spans of deep time. As we continue our journey through deep time, we arrive at our final contemplation of what Pangea's story means for our understanding of Earth's past, present, and future, reflecting on the cycles of change that have shaped our planet and continue to influence our world today. The ancient supercontinent that dominated our planet for over 100 million years offers us profound insights into the nature of change, continuity, and the remarkable resilience of life itself. Pangea represents more than just an interesting chapter in geological history. It reminds us that our modern world, with its familiar arrangement of continents and oceans, is neither permanent nor unique. The earth beneath our feet has experienced many different configurations over its long history, and it will continue to change long after human civilization has become part of the geological record. When we look at our current world through the lens of Pangean history, we gain a deeper appreciation for the complexity and interconnectedness of Earth's systems. The climate patterns we experience today, the distribution of life across different continents, even the shapes of our coastlines, all carry the influence of ancient processes that began when Pangean was assembling, thriving, and eventually breaking apart. The story of Pangea also helps us understand that change and stability are not opposites, but rather different aspects of the same planetary processes. While the supercontinent appeared stable to any creatures living on it, it was actually part of a dynamic system, constantly responding to forces from deep within the Earth. What seemed permanent was temporary, yet what seemed temporary thin, the gradual shifts and adjustments created lasting impacts that persist today. The cycles of supercontinent formation and breakup appear to be fundamental features of how our planet works. Scientists have identified evidence for several supercontinents that existed before Pangea, suggesting that these great assemblies and separations happen repeatedly over Earth's history. Each cycle takes hundreds of millions of years to complete, far longer than any individual species exists. Yet these cycles help drive the long-term evolution of both life and landscapes. Looking toward the future, scientists predict that the continents will continue their slow dance across Earth's surface. The Atlantic Ocean, which began as tiny rifts in Pangea, continues to widen by a few centimeters each year. Meanwhile, the Pacific Ocean is slowly shrinking as the continents around its margins move together. Australia is drifting northward toward Asia, while Africa is gradually moving closer to Europe. These current movements suggest that our planet may be in the early stages of assembling the next supercontinent. Computer models suggest several possible scenarios for how this might happen. One possibility, which scientists call Pangea Ultima, envisions the continents coming together again in roughly 250 million years as the Atlantic Ocean closes and the landmasses reassemble in a new configuration. Pure Verse, another scenario, called Amasia, suggests that the continents might converge near the North Pole, creating a supercontinent quite different from Pangea in its shape and orientation. A third possibility, Novo Pangea, envisions the continents gathering around the equator as both the Atlantic and Pacific Oceans close simultaneously. Of course, these predictions extend so far into the future that they represent educated speculation rather than certain knowledge. The forces that drive continental drift are influenced by many factors, and small changes in deep Earth processes could alter these long-term predictions significantly. What seems certain is that the continents will continue to move, and eventually they will likely come together again in some new arrangement. The formation of future supercontinents will bring changes as profound as those that accompanied Pangea's existence. New mountain ranges will form where continents collide. Ocean currents will be reorganized as seaways close and new ones open. Climate patterns will shift as land masses move to different positions relative to the poles and equator. Life will face new challenges and opportunities as habitats change and new connections form between previously separated ecosystems. Yet, despite these dramatic changes, the fundamental processes that govern Earth's systems will remain the same. The water cycle will continue to move moisture from oceans to land and back again. Plate tectonics will continue to recycle the seafloor and build new mountains. Life will continue to adapt, evolve, and diversify in response to changing conditions. The same forces that shaped the Pangean world continue to operate today and will continue operating in future supercontinents. This continuity of process amid constant change offers a perspective that can be both humbling and reassuring. Our human time frames, measured in decades and centuries, are brief moments in the longer rhythm of planetary change. The challenges and concerns that dominate our daily lives occur against a backdrop of processes operating on timescales that dwarf human experience. Yet this long-term perspective doesn't diminish the importance of our current moment in Earth's history. If anything, understanding the deep history of our planet helps us appreciate the remarkable circumstances that have created the world we inhabit. The climate that supports human civilization, the distribution of natural resources, the biodiversity that enriches our planet, all of these features have been shaped by the long history of continental drift, climate change, and evolution that began long before Pangea formed and continues today. The Pangean world, with its extreme climates, unique geography, and alien life forms, demonstrates Earth's capacity for supporting dramatically different conditions than those we experience today. This suggests that our planet has the potential for many different stable states, each capable of supporting rich and diverse ecosystems adapted to their particular circumstances. Understanding Pangea also provides perspective on the concept of environmental change. The transformations that occurred during the supercontinent's existence were far more extreme than any changes happening in our current world. Yet life not only survived, but thrived and diversified. This doesn't minimize the significance of current environmental challenges, but it does illustrate life's remarkable capacity for adaptation over long time periods. The fossil record of the Pangean world shows us that even the most severe environmental crises, like the Great Dying at the end of the Permian period, can ultimately lead to new evolutionary opportunities. The recovery and diversification that followed that great extinction set the stage for the rise of dinosaurs and eventually mammals. Crisis and renewal appear to be recurring themes in Earth's long history. As we reflect on the world that was, we might also consider what traces of our current world might survive into the distant future. Just as we can read the story of Pangea in rocks, fossils, and continental arrangements, future geologists might be able to decipher evidence of our time. The materials we've moved and concentrated, the changes we've made to atmospheric composition, and the species we've caused to go extinct or helped to spread will all leave signatures that could persist for millions of years. The study of Pangea reminds us that we are part of an ongoing story rather than witnessing something unique or unprecedented. Our planet has experienced many different worlds, each with its own character, challenges, and opportunities. The Pangean world was just one chapter in this long narrative, remarkable for its scale and duration, but part of a larger pattern of change and adaptation. The deep time perspective offered by Pangea's story can be both fascinating and meditative. When we contemplate the vast spans of time involved in continental drift, the patient processes of mountain building and erosion, the slow evolution of climate and life, we enter a realm where human urgency gives way to planetary patience. The Earth operates on its own schedule, following rhythms that connect our present moment to an ancient past and an unimaginably distant future. Perhaps most importantly, the story of Pangea reminds us of our connection to the deep history of our planet. The carbon in our bodies may have cycled through Pangean atmospheres. The rocks beneath our feet may preserve memories of ancient Pangean landscapes. The ocean basins that separate modern continents began as tiny cracks in the supercontinent's surface. We are not separate from this ancient world, but rather products of the long chain of processes that began with its formation and continue today. As we conclude our journey through the world that was, we can rest in the knowledge that Earth's story continues. The same creative forces that built Pangea sustained its remarkable ecosystems and eventually transformed it into our modern world are still at work. Continents continue their slow dance, life continues to adapt and diversify, and our planet continues its patient work of change and renewal. In this long view of planetary time, our current moment appears both infinitely brief and deeply significant. Brief because it represents just an instant in the 4.5 billion year story of our planet. Significant because we are among the first creatures in Earth's history to understand and appreciate the full scope of this remarkable story. We can look backward through deep time and forward into an uncertain but wonder-filled future, carrying with us the perspective that comes from understanding our place in the great continuum of planetary change. The world that was teaches us about the world that is and the world that will be. In the quiet contemplation of these vast processes, we find both our humility and our wonder, both our connection to the ancient earth and our responsibility as conscious participants in its ongoing story.